15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on the Space Nuts podcast, episode 213. My name is Andrew Dunkley, your host, and joining me as always is astronomer at large, Fred Watson. Hello, Fred.
Morning, Andrew. How are you doing?
I am well. You have set a cat amongst the pigeons, my friend, or more to the point, a rooster amongst the hen house, given that our good friend Gregory Peck made an impromptu appearance on the show last week, and people are loving him.
Well, he's lurking around outside, so there might be more of Gregory today. I don't know. He's deafening from where I sit. I can tell you, it's we almost need earplugs when he really gets worked up. Hopefully,
well, there are demands for photographic evidence. So,
well, I've talked to his agent, and she's going to talk. I think our people are going to talk to your people. We'll see if we can provide that. There is even talk of T-shirts. I know, I've heard that.
Someone actually brought that up as it could become the new logo. Space Rooster. Who knows? Yes, and I understand.
He is a very
sorry.
I have to say, he's a very handsome rooster. So he'll do very well when he appears on T-shirts. I'm sure.
Okay, can't wait. All right. Well, if we do manage to do some kind of photographic deal, we will certainly post that photo on the Space Nuts podcast group on Facebook for those who have requested such. I understand you have a new addition to the family as well.
Yes, we sadly, as you know, lost our beloved cat, Mandu. But there is a fairly largish, I have to say, it's probably a year-old kitten that now frolics around the place, whose name is Muscat. It's just part of the deal. It's because Marnie's business, of course, was travel, and these are all destinations that she's taken groups to and things like that. We were in Muscat last year, in fact. But anyway, Muscat is certainly not a Mandu, but he does have a character of his own. I'm sure. Yes.
Well, if he makes any impromptu appearances, he will be most welcome.
Yeah. He's fast asleep next to me at the moment. Does a lot of sleeping.
Yeah, that won't last.
Teenage behaviour, that's what it is.
Mm-hmm. Okay, on today's edition of Space Nuts, we're going to discuss the launch of NASA's mission to Mars. Now, it's due to leave Thursday US time, which will be past tense by the time this particular podcast is out, give or take, and weather permitting. But we do want to talk about that upcoming mission. And we want to talk about the RAVE project. Now, this is a project where Fred may have a bit of an inkling as to what goes on, because he was the project scientist. So one would hope. But stranger things have happened. Politics is a good example. Anyway, we'll look at the RAVE project. I think it's focusing on movement of stars, if I'm not incorrect, which is not uncommon anyway. And audience questions from Martin in Austria and Paddy in Sydney about the International Space Station, space junk, and creating a magnetic field to protect astronauts from radiation. All those sorts of things are going to be discussed today on the Space Nuts podcast. Now, Fred, let us begin with this 2020 Perseverance mission to Mars, which by the time this podcast is released will hopefully have begun.
We hope so. That's right. As you know, we've talked about this before, Andrew. Of course, there's a window for launch. And that window it started about a couple of weeks ago and extends into August. The United Arab Emirates and the Chinese have already taken advantage of this window, which gets you to Mars with minimum energy orbits. That's the whole point of it. So the Perseverance rover is the last of the trio. We have a launch window that begins actually on Thursday, the 30th of July. And as far as I know, NASA is still go for launch at that earliest opportunity. It's 4:50 a.m. Pacific Daylight Time on the 30th of July. That makes it, if I did my calculations correctly, sort of 8 o'clock in the evening here in Eastern Australia. So we hope all will be well. As things stand now, we're 1 day, 12 hours, 33 minutes and 30 seconds into the countdown. That is the countdown. It's counting down, and we hope to bring good news in the next edition of Space Nuts. But I thought it would be worthwhile just reminding all our esteemed listeners what this is about. The spacecraft is a rover of I guess a similar design to Curiosity. Obviously, these things evolve from one step to another, but it's certainly true that when you look at Perseverance, it owes a lot to the design of Curiosity. 6 wheels, weighs approximately a ton. It's powered by the traditional RTG, radio isotope thermoelectric generator, little boxes of plutonium. They sit on the back of the spacecraft, and then there's the mast with the cameras on top. There's a whole lot of apparatus on the robotic arm, which is at the front of the vehicle, and uniquely, as you and I have spoken about before, it carries a helicopter, which is powered by a solar panel. The helicopter called Ingenuity. Helicopter weighs about 2 kilograms. It's not a flimsy thing. This is a fairly solid device. One little factoid that we didn't discuss when we talked about Ingenuity, the helicopter, a little while ago, is that its 4 carbon fiber blades will spin at 2,400 RPM. That's a huge speed. And I guess that's necessary in order to bite into Mars's rarefied atmosphere, less than 1% of the atmospheric pressure that we have here on Earth.
And from what I've read about Ingenuity is that it's going to pave the way for future exploration of Mars. It could well be the next phase of interplanetary exploration, because helicopters will be able to go to places that rovers cannot, and they'll be able to get there faster.
Exactly.
So it could be quite a momentous achievement if they can make it work, and I don't doubt that they will. I mean, yes, you and I have talked about some of the catastrophic failures of the past in terms of certain probes missing the mark or hitting too hard, and those are the risks you take. But most missions seem to do rather well, and launching a helicopter on another planet. I mean, who'd have thought about it 20, 30 years ago? But now it's going to happen. Yeah. Fingers crossed, it's going to happen.
Yeah. So exactly as you've said, the reason for the helicopter, certainly in this case, and they may be used for different things later on, but it's just to scout out the terrain ahead of the rover, to look for places of interest, of geological interest within the rover's range, to look more especially for obstacles. If the rover comes over the brow of a little hill and then finds that the way ahead is blocked by boulders or something of that sort, it would be nice to know about that before you bother to drive up the hill. And so that's what the Ingenuity helicopter will be used for. I'm really looking forward to seeing what kind of imagery we get from it, what sort of performance it has. And just two final points on this. Of course, the whole point of Perseverance is the idea of looking for signs of past or present life on Mars. That's why it has its drill, to try and extract core samples and things of that sort. And also, I've forgotten what the other thing was I was going to tell you. Probably that it's due to land round about February next year.
I was going to ask you how long this journey will take. It is a long trip to Mars, isn't it?
It's quite a way, that's right. But all systems are go at the moment. As far as I know, everything is on track, as I believe it is with the 2 other spacecraft that are already on their way to Mars.
Yeah, if you're going to take the kids to Mars, make sure you're stocked up on those in-car entertainment DVDs or iPad downloads, because they're going to get bored real quick. Are we there yet? I think will happen many, many times. But the other thing is the landing point, which you and I have mentioned. They've chosen, I believe, a river delta area.
Yes, that's right. Jezero Crater is the name of the location. And it's got a river delta there. So there was at one stage in Mars's history flowing water over this shallow region within this crater. And it's thought that river deltas are very efficient places for the dumping into the terrain of any kind of biological material. River deltas on Earth are very rich in biological material that's carried down by the river. So the hope is that there might be evidence in that region of perhaps past life. You never know. There might be signs of metabolic activity there now, but past life, I guess, is what is the focus. One other thing just about Perseverance is that it will gather samples as well, which are intended then in a future Mars mission to be brought back to Earth for analysis. So it's the kind of part one of something even more ambitious.
And the other thing they're doing, which sort of hasn't really been raised too much in the media, although I spotted it the other day and I had to mention it on the radio, is they're taking back a rock from Mars that landed on Earth 600,000 years ago.
One of the Martian meteorites, that's right, of which there are about 300 known, I think. It's been taken back as a sort of calibration sample for their experiments. Fabulous stuff. Imagine that, a meteorite that came from Mars being taken back there to be left on the surface.
Yes. And they'll probably go, what are we supposed to do with this? We got rid of that ages ago. We don't want it. Take it back.
Look what's come back. Oh, my gosh.
We've got plenty of them.
Yeah.
But very exciting. And with 3 missions bound for Mars, there'll be a lot to talk about, well, next year, basically, when all of this starts to unfold, I imagine.
Yeah, we'll have to change the podcast to Mars Nuts, Andrew, rather than just Space Nuts.
Yeah, maybe. We'll do a special Mars Nuts edition for 3 months or something.
Yeah.
While all the data comes out.
Yeah.
All right. We watch with interest, and hopefully by the time you hear this, that mission will be nominal and headed for Mars. You're listening to Space Nuts with Andrew Dunkley and Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated number 1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments, and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Once again, just saying hello and thank you to our social media followers, whether it's on Facebook through the official Space Nuts Facebook page or the Space Nuts podcast group. We are on Twitter. We are on Instagram. We are on YouTube. And if you are interested in downloading the podcast via YouTube, we're looking to get our monthly download figures to around 4,000. And or you can listen on your favourite podcast distributor. But social media seems to be a place where we gather a lot of followers, and particularly with the Space Nuts podcast group, it's a good avenue for you to talk to each other. And I notice it's a very, very busy group indeed. And I occasionally poke my head in and have a look around and see what everyone's talking about. But whatever platform you listen to us on, thank you for supporting the Space Nuts podcast. And you can also show that support through Patreon or one of the platforms where we give you the opportunity to contribute to the show financially through Patreon, Supercast or Acast. And it can be for as little as $3 a month. It's purely voluntary, but we're getting more and more people sign up with that option every week. So we thank you for supporting. And of course, as a financial contributor or as a patron, you do get a few extra benefits, including bonus material, which will pop up on whatever platform you follow us on, which I hope you're finding most enjoyable. We're certainly having fun putting it together. Now, let's have a bit of a rave with Fred, who is wanting to talk about the latest information from the Radial Velocity Experiment, otherwise known as RAVE. Fred, you're pretty close to this one.
Indeed, yeah. I wasn't actually the project scientist. That was the role of one of my colleagues in the University of Ljubljana in Slovenia. His name is Tomáš Svita. My job was to be the project manager. So RAVE was actually quite a large consortium of something like 60 scientists from 20 institutions internationally, many of them located in Europe. In fact, it was led by, and I suppose technically still is, although I'll get to that in a minute, it's led by Professor Dr. Matthias Steinmetz, who is the head of astrophysics at the Leibniz Institute for Astrophysics in Potsdam in Germany. So Matthias, Tomáš, and myself were the three, what you might call managers of this project, but there was also a board, an executive board, which we're all members of, and then the consortium itself, as I said, 60 scientists. So what is it? It is a project which had its inception back in 2003. I remember a meeting on a chilly morning in Cambridge, UK, where we discussed the possibility of using the United Kingdom Schmidt telescope at Siding Spring Observatory here in Australia, and was equipped then with a robotic fiber optics machine called 60F, that stands for 6-degree field, the field of view of the telescope, which would allow you to gather information on the velocities of stars, accurate velocities for stars. And this proposal was actually on the back of a spacecraft that was being planned. Now, I can't remember. I think it might have been FAME, the spacecraft that was being proposed by the German Space Agency. And the idea was that the spacecraft would make measurements of the velocities of these stars across the line of sight, and we would then, from the ground, do the equivalent, but along the line of sight. And if you can combine those, you get what's called the true velocity of the star. So the whole idea of this radial velocity experiment, and radial velocity is just the velocity of a star along the line of sight, was to build a database of stars using the Schmidt telescope. And indeed, it got kicked off. It went through all kinds of tribulations in its early days, but we started pilot observations in 2003. In 2005, the RAVE project became the only project that the UK Schmidt telescope was undertaking. So it was undertaking it throughout the whole year rather than just on selected dates each month. And the project grew. It actually grew in many ways. The initial idea was to gather velocities of stars. And I might just add, I've got a vested interest in this, but I'm not boasting about it from any personal point of view. But we did great things, there's no doubt. When we started, the total knowledge of the total sum of stellar star radial velocities was about 20,000 that had been gathered for the previous 150 years. And within the first year, we had, I think, more than doubled that. We'd gone to 40 or 50,000. I can't actually remember the number. But it became quite obvious that this was a very effective way of improving our knowledge of the velocities, the motions of stars in the sun's neighborhood in our galaxy. And that's why the project then kind of took off. And basically, we observed for round about 10 years. It was the final observations were made by somebody called Fred Watson on I think it was the 4th of April 2013. It was in the wake of the Wombalong fire that nearly took out the observatory. I did 4 nights of observations in the April of that year just to prove that it wasn't the fire that brought the project to an end. In fact, we essentially ran out of funding. However, in that 10 years, we measured 518,387 spectra, that means the data points, for 451,783 stars. There you go. That's the final number. So, as I said, the observation stopped in 2013. 7 years later, what is happening is the final, basically the final catalogue of all these data has been released. In fact, it was released end of last, I beg your pardon, no, it's last week, 27th of July, 2020. That was when we released what's called DR6, the 6th data release of the RAVE catalogue. And it's the sort of final product. This is the end product of what the survey has been all about. And I'll shut up for a minute so you can ask a question. But when I start again, I might just give you some hints into what has been discovered from that, Andrew.
Well, that was going to be my question, because you've done all this work over such a long period of time, and I'm sure that you've been able to crunch the data and come up with some revelations. And I'm just looking at some of the information that's been released, and they're talking about things like how fast a star has to be moving to escape gravitational pull. But I'm quite intrigued by the results confirming that dark matter dominates the mass of our galaxy. I mean, it's something we don't know much about, but you've been able to confirm that it is a dominant force in the universe.
Yeah, that's right, and certainly in our own galaxy. So what you're doing is you're using the speeds of stars to essentially reveal something about the gravitational field in which they're moving. That's basically how you it's one of the ways that you can tell what sort of gravitational pull stars are feeling. And sure enough, we get this same result, that most of the mass of our galaxy is in dark matter. That other result you mentioned, it plays into the same idea, in fact, because the idea of determining the minimum speed needed for a star to escape the gravitational pull of the Milky Way. It's actually one of the first papers that was produced from RAVE back in about 2004, very early result. What's called the escape velocity of the galaxy. That gives you a mass of the galaxy. But of course, that mass includes not just the stars you can see, but also the dark matter. And in more detail, RAVE has shown that the disk of our Milky Way is wobbling slightly because of the satellite galaxies, like the two Magellanic Clouds, the way they are interacting with our galaxy. It sort of has wobbles in it. And we've also found streams of stars which are probably the remnants of dwarf galaxies that have been pulled apart. The first one that was found, it's probably back in about 2006 or thereabouts, was something called the Aquarius stream. It was the dawning of the stream of Aquarius that was the title of the paper, I think. So that's, dwarf galaxies that have been ripped apart. They have merged with the Milky Way, but we still see their evidence in the movement of the stars. So it was a pretty neat project, I have to say. And let me say that I am very honoured to have played a part in it. My role was essentially supervising all the observations. It was a team of half a dozen of us who did the observing. I was managing that group as the astronomer in charge of the observatory, but also as the RAVE project scientist, project manager, I beg your pardon. I spent a lot of time worrying about budgets and where money was coming from. I spent a lot of time worrying about the fact that the fibers in our fiber optic machine kept breaking and all sorts of stuff. It's why, Andrew, I've got no hair left virtually, that RAVE put a big load on my shoulders. But honestly, it was worth every lost hair of it, because well over 100 top-class scientific articles have come from the RAVE project, and that's just a brilliant output. So
Yes,
it's kind of RIP RAVE, because this sixth data release really represents the end of the project, and the fact that those data are now public. Any of our listeners could go and access them. You've got to go and find them at the Institute for Astrophysics in Potsdam on their website, but it's pretty easy to do if you just Google RAVE and it'll take you straight there, or to some party or other that might have the same name.
And I suppose, Fred, with all the information you've collated and released, it may well pave the way for future studies, and we may, through other avenues, learn a heck of a lot more about stars and maybe even dark matter.
In fact, those studies are already underway, Andrew. You're quite right. Yeah, so a similar survey, but in a little bit more detail, because it's a bigger telescope. That's going on with the Anglo-Australian telescope, the 3.9-metre telescope at Siding Spring. That's called GALAR. GALAR is Galactic Archaeology with Hermes, and Hermes is another of these fibre optic spectrographs, but working in a different way. But the one thing that really has, I think, sort of shone the way ahead, and actually has allowed RAVE data to be used in a completely new way. That is the Gaia spacecraft. Gaia is an ESA spacecraft which is measuring the positions of stars with micro-arc-second accuracy, and you can combine the data coming from that with the RAVE data to get really extraordinary detail on the way things are operating in our galaxy, not just the movement of stars in the galaxy, but their chemistry, their temperatures, surface gravities, all of that stuff comes from this combined set of data. So it's really a really powerful tool.
And you also, as a part of it, tried to find some of the very, very first stars. I mean, that must have been interesting and difficult, I imagine.
It is. It's exciting stuff as well. So what you're looking for is stars that have got a very low metal content in their atmospheres, principally iron. The lower the amount of iron there is in the atmosphere of a star, the earlier it must have been born in the history of the universe, because iron is enriched gradually throughout the history of the universe. So RAVE had the potential to find those. In fact, I think a couple of times stars found with RAVE were record holders for the earliest known star. That's a movable feast. It's like the most distant known object. It's something that keeps changing as new technology comes along. But yes, it pointed to very early stars, clues about the earliest epochs of star formation and the chemical evolution in the Milky Way, as the press release says.
Indeed. Yeah, fantastic. Well done, Fred.
Thank you. I'll take
to
credit.
you and the whole team. It's been a fantastic project. Yes. And it's good that you could have a rave about RAVE.
Oh, we had many.
You've got to be You've got to be able to blow your own trumpet occasionally, and I mean that's what you do. I mean you work in this arena, and I think people would be really keen to hear about some of the direct influences and hands-on work you've done. So fantastic effort.
Thanks very much.
You are listening to the Space Nuts podcast with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
As always, I would encourage you to visit our website where you can go shopping. We have a Space Nuts shop, we have a Space Nuts bookshop, and you can record your audio questions through the AMA tab on the spacenutspodcast.com website. It's a very easy URL. You'll notice it'll change once you load it. Just ignore that. It's an illusion. Spacenutspodcast.com is where you'll find our official Space Nuts webpage, and from there you can have a look around, listen to all our episodes, and if you do want to ask an audio question, all you need is a device with a microphone plugged in, and you can most certainly send in audio questions, but we'll still take them in text form. More than happy to do that if you don't have the capacity to record, or you're a bit embarrassed about your voice, or you just don't want to. There's all sorts of reasons. Speaking of audio questions, Fred, let's get stuck into some of these. We've got one from Martin, who is in Austria.
Hello, Andrew. Hello, Fred. This is Martin from Austria. I have a question about the ISS. So I can observe it with the naked eye, but it varies quite a bit. So my question is, why does it vary that much? Is it because of orbital adjustments the ISS has to do? If so, how do they do that? And what are the things they have to bear in mind? Do they have to look out for space junk or satellites or other stuff? It would be good if you could explain that. And been a fan and listener of your show for 2 years. Keep up the good work. Greets from Austria. Bye.
There you go. Thank you, Martin. Great to hear from you. And he's asked some interesting questions. I suppose, Fred, it's something we have touched on before, because in the not-too-distant past, they did have to actually move the ISS because of a potential collision with space junk, which is something Martin asked about. But I suppose the first part of his question was about the variation in the observability of the ISS, which you can see with the naked eye, but sometimes it's more difficult than others. Why would that be?
Yeah, yes, exactly. It's the brightness that's varying. And actually, part of what is the reason for that is exactly what Martin says, because of the orbital adjustments. So the International Space Station, its nominal altitude is about 400 kilometers, but it can't just stay at that height if you don't do anything, because it's such a huge object with these gigantic solar panels and acreage of real estate as well. It actually interacts with the very tenuous atmosphere there is even at that height. So if you don't do anything, it just gradually reduces in altitude. And so what happens is exactly as Martin suggests. There are orbital adjustments. What the mission controllers do is essentially they've got rockets, station-keeping rockets they're called. Basically, these are the thrusters that actually boost the International Space Station to a higher orbit. If I remember rightly, on the Heavens Above website, I don't know whether it's still there, but it certainly used to be, heavens-above.com, I think is the URL. That has a chart of the altitude of the International Space Station over time, and it's a kind of sawtooth graph, because the thing gradually comes downwards and then they boost its orbit upwards slightly to make the sawtooth shape. Now that is they're probably changing the altitude by 50 kilometers or something like that. I can't remember the exact details, but that's enough to because of the geometry of the way we see it, the fact that we are seeing the space station illuminated by sunlight, and that's that 10% or 20% or whatever it is change in altitude is enough to change the brightness of the space station that we see. But I think the biggest cause of variability is just its the attitude that the space station has as it transits across your field of view, because it is shining by reflection. And you can imagine these enormous solar panels, they're not what you call specular reflections. They're not acting like mirrors. They're basically just scattering the light. But depending on the exact orientation of the spacecraft as it flies overhead, you're going to see some difference in the amount of light it's reflecting. So it is quite variable, exactly as Martin says. It's always pretty bright too. It's certainly the brightest of all the artificial satellites around the Earth. I'd have to tell you, I always get a buzz when I see it going past. It's such an emotive thing that that 400 kilometers up there's an international crew of experts actually doing work in space. I think it's a fantastic thing.
Oh, it is, yeah. And 400 kilometres isn't really that far. I mean, you and I are almost that far apart.
Yeah, that's right. Yeah.
So when you think about it, that's not a great distance in the scheme of things. So although from up there, the view, oh my gosh, I would just love to go up there just to take a look at Earth from that vantage point. I think I don't even think photos do it justice. I think the naked eye, the human eye view from the International Space Station, especially if you were outside, would be just mind-blowing. I envy those people. I know they've worked hard to get there, and it's all business, but I don't think they'd get sick of it. Do you?
No, I think they probably quite enjoy their job.
Yes, indeed. Now, he also mentioned space junk.
Yeah.
And space junk is an ongoing problem because there's just more and more of it turning up out there. And with so many satellite launches happening at the present time, there's the capacity for more space junk, and collisions are always a factor that we need to be aware of.
Exactly, that's right. So, yes, as Martin said, do they have to look out for space junk? They do. That's all done through mission control. The thing, things like the NORAD radar. These are the facilities that actually allow us to track debris down to about 100 millimeters across in orbit. And as you said at the beginning there, Andrew, there are occasions, probably 2 or 3 times a year, when the orbit of the space station has to be adjusted slightly because there's a danger that it might come within range of some piece of space junk that's in a similar orbit. Of course, the smaller stuff that's not able to be tracked, that's something you can't really guard against. That's why the space station itself is fairly solid. Just one final thing: if the space station is under threat from a piece of space debris, they would adjust the orbit to try and avoid it. But there is also I know that astronauts have congregated in the Soyuz escape modules just to be safe if there is an encounter like that.
Yeah, and you can never be too careful in space. It, as quoted by the character in The Martian, space does not cooperate.
It's very unforgiving. That's right.
Yes, indeed. Very hostile environment as well. Martin, thank you for your questions. Very enlightening, and glad we could talk about some of those things. Let's move on to our next question from Paddy in Sydney.
Good morning, Fred and Andrew. It's Paddy from Sydney, roofer. Sorry to hear about Mandu, Fred. That's really sad news, mate. Anyway, I've got a question. I did ask this before, but I thought I'd just do the audio. Anyway, just with molten lead and molten metals or dissimilar metals, using them, spinning them around, boiling them up, would that be a way to create a magnetic field to protect astronauts? Is it possible we can do that? I did watch a documentary recently on how they were trying to do that, but with a different metal with a really lower melting point. Not sure if that's possible, but if it'd be strong enough magnetic field to protect the astronauts. But yeah, that's about it. Have a great weekend, and may the force be with you.
Thank you, Paddy. Nice to hear from you in person. Yes, Freddie, he's a roofer. And he I think, was the one that asked us about roof tiling on Mars protecting astronauts.
That's right.
Right. So now the question is, can we create magnetic fields to protect astronauts in space using molten metals?
I do like Paddy's thinking, because it's always about how we create an environment that will protect astronauts, particularly on Mars, but also heading to Mars. And I haven't actually heard of this idea of using fluid metals to create the magnetic field. I mean, that's clearly how the Earth's magnetic field is created, by the sloshing around of molten iron in the core. I think in practice, it is going to be down to using much more conventional shielding to protect astronauts in deep space. Lead is a pretty good way of stopping the radiation from the sun penetrating inside a spacecraft to astronauts, but lead is pretty unforgiving as well, just like space.
And it's very heavy, so getting it up there would be a nightmare.
Yeah. So I know that some of the designs that are being suggested actually use water as the shielding. So maybe you've got a water tanker in orbit, and you send your spacecraft up there, and then you fill up the tanks to provide the shielding. I haven't followed that in detail, and Paddy's suggestion is interesting. If you've got a low melting point metal that was capable of generating a magnetic field, that would be a really interesting way to do it. But I haven't really been following this, so I shouldn't comment without actually looking at what results people are suggesting there. But great thought. Thank you. And I will check up on that, Paddy.
Yeah. What about mercury? Would that work?
No, I don't think so. I don't think mercury would work. I think while it doesn't necessarily have to be a ferrous metal, I think it's got to have certain characteristics. Look, I'm guessing here, Andrew, and making this up as a go along, but I will check up on it, because it's such an interesting thought.
It is. How do they protect the astronauts on the ISS, to bring today's two questions together? What are the protections there from radiation?
Well, they don't really need it, because they're within the geomagnetic bubble that the Earth itself provides.
Oh,
the radiation.
Okay. So once you get outside of that and do a bit of a long haul trip, you're starting to find yourself exposed. What about going to the moon? Are they exposed in that trip?
Yes, they are. And what's sort of helped in that regard with the astronauts, the Apollo astronauts, of course, they're only in that environment for a week or so out of Earth orbit, and all the risks were thought to be tractable for relatively short periods of exposure like that. But I think the problem is, when you are talking about a Mars flight, then it's at least 6 months, and that's a very different kettle of fish from 6 or 7 days in the full radiation field of the sun.
I'm starting to think the solution lies in the alien conspiracists who wrap aluminium foil around their heads. I think that might be the go.
Well, I've got that around my head all the time, Andrew. It's, just to make sure,
Yeah, maybe. All right, Paddy, thanks for the question. You've got Fred thinking, and he might have to do some homework to come up with something on that. But it is really clever thinking, right outside the box. So good on you, mate. Good to hear from you too, Fred. I think that's just about it for another week. I'd certainly encourage people to send their questions in via our website. Always good to hear from you, or whether it's in written form or verbal. So please do that. You can record via the AMA tab, which I mentioned earlier, at spacenutspodcast.com. Thanks as always, Fred. Another episode in the can, as they say in the industry.
Indeed, that's right. And I'll have to chase up Gregory, because he's a bit silent today. I think he's across the paddock somewhere. So we'll see what happens next time, Andrew. Thanks very much.
No, great pleasure. Thanks, Fred. Fred Watson, astronomer at large, part of the team here on Space Nuts. And thank you for your company. Looking forward to catching up with you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.